Previously, in Part 1, we covered the basics of Python's built-in data types that are scalar in nature, meaning they represent a single value. Yet, we commonly have to work with many objects and values at once. In Part 2, we will explore the sequence and set types that can hold multiple Python objects and values. We will start with Python strings, which are used to represent text and are usually introduced as a scalar type. We intentionally left them out of Part 1 because they can also be thought of as a sequence of values that represent characters, which is exactly how Python defines them. In this channel, we bridge the gap between writing Python and shipping production-ready Python, covering the essential ideas and tools you need to get there. Python sequences represent finite and ordered values. Strings represent text as a sequence of characters. But unlike many other programming languages, Python does not have a separate character type. Instead, Python represents each character as a string of length 1. Under the hood, each character is just a number. You can get the number for a character using the built-in ORD function, and you can get the character for a number using the built-in char function. This number is determined by the Unicode standard, which assigns every character a unique number called a Unicode code point, usually shown in hexadecimal notation. Unicode has space for over 1 million possible code points, and roughly 300,000 are currently assigned. It covers letters from writing systems around the world, numbers, punctuation, accent marks, mathematical symbols, currency symbols, technical symbols, historical scripts, emoji, control characters like newline and tab, and private use slots for custom meanings. Since strings are sequences of characters, indexing and slicing them gives you back a string. This is also why you can iterate over a string and get back one-character strings. Strings are immutable, so any string operation creates a new string object in memory. The empty string is the only string of length 0, and also the only falsy string. Strings are closely related to another immutable sequence type called bytes, which represents sequences of bytes, or 8-bit integers. They're often used when working with binary data, like files, network messages, or encoded text. You can create a bytes object from a string using the encode method. We won't go into the details of the different encoding methods, but the default Python uses is UTF-8, a scheme for mapping Unicode code points to bytes. You can also write a bytes object directly as a literal using a string with a leading B. Note that a bytes literal can only contain ASCII characters in the source, which are the plain English letters, digits, and common punctuation. For anything else, such as accented letters, emoji, or non-Latin scripts, you must use the encode method or the bytes constructor. The length of a bytes object is the number of bytes, which may differ from the number of characters in the original string if it contains non-ASCII characters. For ASCII text, all three approaches to creating a bytes object produce equal results. We saw that indexing or slicing a string object gives you back a string object. This isn't the case for bytes. Indexing a bytes object gives you back an integer representing the byte value at that position, while slicing a bytes object gives you back another bytes object. The empty bytes object is the only bytes object of length 0, and also the only falsy bytes object. Strings are immutable sequences of characters, which are all of the same string type. Bytes are immutable sequences of bytes, which are all of the same integer type. What if we want to have an immutable sequence of Python objects that can be of other types or even a mix of types? Python tuples can do that. They're often used to represent fixed collections of objects that belong together, like the coordinates of a point or the RGB values of a pixel. Because they're sequences, like strings and bytes, they also support indexing and slicing, and you can iterate over them. You can create an empty tuple with empty parentheses or using the tuple constructor. A small gotcha for creating a tuple with one element is that you need to include a trailing comma. Otherwise, it'll be interpreted as the value itself. In fact, the parentheses are optional for creating non-empty tuples, and the comma is what actually creates the tuple. Tuples are immutable, so you can't change their contents after they're created. You can't add, remove, or modify elements in a tuple. Like other sequences, the empty tuple is the only tuple of length 0, and also the only falsy tuple. So far, we only looked at immutable data types. Our first mutable sequence is the Python list. Lists can hold any type of Python objects. So they're like tuples, but with the added ability to change their contents after creation without creating a new object in memory. You can use mutable list methods like append and insert to modify them in place. They're often used to represent collections of items that are dynamically changing. They also support indexing, slicing, and iteration, just like other sequences. A common source of confusion is that the mutability or immutability of an object is a shallow property, meaning it only applies to the collection itself, not to the objects it contains. That's why you can have a list that contains immutable objects like we just saw, or a tuple that contains mutable objects like a list. If you have a tuple that contains a list, you can modify the list inside the tuple, since a list itself is mutable. But you can't change the tuple itself to refer to a different list or any other object. Loosely speaking, a list is a mutable version of a tuple, whereas Bytearray is a mutable version of bytes. You can create a Bytearray from a bytes object, from a string with an encoding, or from an iterable of integers from 0 to 255, all using the Bytearray constructor. Unlike bytes, Bytearray has no literal syntax. That covers both immutable and mutable sequence types. The set types come next. Python sets represent unordered collections of unique values. So, unlike sequences, they can't be indexed or sliced. However, you can still iterate over them and use the built-in len function to get the number of elements in a set. Because there's no beginning or end to a set, we don't append or insert elements at a specific position. Instead, we add elements to a set using the add method and remove elements using the remove method. Sets are often used for fast membership testing, like we saw in part 1, and for removing duplicates from a sequence. They're also useful for performing mathematical set operations like union, intersection, difference, and symmetric difference. Set types also include Frozenset, which is an immutable version of a set that you can't modify after creation. You can create a frozen set from any iterable using the Frozenset constructor. We mentioned in part 1 that sets are dramatically faster than lists for membership testing. The reason is that sets are implemented as hash tables, which allow for constant average time complexity for membership testing. When you check if an element is in a set, Python computes the hash of the element and uses it to quickly find the corresponding bucket in the hash table where the element would be stored. If the bucket is empty, the element isn't in the set. If the bucket contains one or more elements, Python compares the element with each of them to see if it matches. Python integers generally have a hash value equal to their value. There are exceptions though. For example, the hash of -1 is set to -2 to avoid the special return value of -1 that the hash function uses to indicate an error. As a side effect, -1 and -2 are a pair of integers that share the same hash, so they'll always collide in a hash table if both are present. But this isn't a problem since they're different values and will be compared for equality when they end up in the same bucket. Hashability has two requirements: a hash value that doesn't change during the object's lifetime, and the ability to be compared to other objects for equality. This is why mutable types like lists and sets aren't hashable, while immutable types like tuples and frozen sets are hashable. So you can have a tuple or list that contains a list, but you can't have a set or a frozen set that contains a list. Let's add one more column to our data types table for hashability, even though it can be inferred from the mutability here. If we revisit the membership testing benchmarks from part 1, something like the following happens at an intuitive level. When we check whether 500,000 is in a set of a million integers, Python computes the hash of 500,000, which is itself, and then takes it modulo some k to find the corresponding bucket in the hash table. If k were equal to 250,000, for instance, then 0, 250,000, 500,000, and 750,000 would all map to the same bucket. Python then checks the entries in that bucket one by one and finds 500,000. On top of a quick hash lookup, we scan at most 4 elements, compared to up to 500,000 in a list. But lookup is only half the story. Building a set isn't free, since every element gets hashed on the way in, which takes longer than building a list. Let's have our benchmarks also report the build time and compare. Building a set costs about 3 to 4 times what building a list does, and roughly the same as one full list scan against a missing target. Both touch every element. The set adds a hash on the way in. So if we have a list and we only need to check membership once or twice, converting to a set is roughly a wash. But the moment we do it more than a few times, the set starts winning. Where exactly is the break-even, the number of lookups at which converting to a set pays off? In the worst case, the break-even sits at 1 to 2 lookups. In the average case, it climbs to about 3. Either way, it's roughly the same regardless of how big the collection is. So should we always convert our list to sets after a couple of lookups? No, definitely not. If we wanted to extract every nanosecond, we wouldn't be writing Python. And the Zen of Python says, beautiful is better than ugly. Simple is better than complex. Readability counts. We can still convert a list to a set when we have a real reason. Or, if performance is really a bottleneck where Python can't help, we can always rewrite that part in C or Rust and call it from Python. This is why numerical computing libraries like NumPy are written in C and provide Python bindings. They can perform heavy computations much faster than pure Python code while still being relatively easy to use from Python. But never forget that premature optimization is the root of all evil. In the first two parts, we covered the scalar, sequence, and set data types. In the next and final part of our data types chapter, we'll cover the mapping types, dictionaries, and frozen dictionaries. Dictionaries are arguably the most important data structure in Python, since the language itself is built on top of dictionary-like structures, and they're used heavily throughout most Python code. See you there.